All right, remember that in an electric field, an insulator becomes polarized. That is, the positive and negative charges, although they can't flow away from each other, do get distorted by the field. The positive charges move in the direction of the field, and the negative charges move very slightly in the direction against the field. This creates an effective net positive charge on one end of the insulator and a net negative charge on the other side. This looks a lot like a capacitor by itself. In other words, it's a sheet of positive charge and a sheet of equal negative charge on the other side. But the polarity of this opposes the electric field. That is, if the electric field is pointing this way, then the capacitor has a field that goes, the quasi-capacitor has a field that goes the other way. All right, we apply some field, it splits the two charges, and then they produce a field which goes from their positives to their negatives, but it will be weaker. All right. These are what we call induced charges. Notice the induced positives are very close to the actual negative part of the capacitor, and the induced negatives are close to the positive plate of the capacitor. The induced field counteracts the capacitor's field, and so makes it weaker. The insulator is called a dielectric, if it's in here, a dielectric. It is just an insulator, but in this context, it always means capacitors are filled with dielectrics. The dielectric is polarized opposite to the field of the capacitor, and the induced field reduces the field. All right, it opposes the field, but is weaker. The ultimate effect is to make the electric field of the capacitor smaller. Note, we don't see any of these microscopic things that go on, so what you would say from a macroscopic viewpoint is that for some reason the electric field is not as strong as you would have expected with the charge that you have. But the presence of these induced opposite charges reduce the effectiveness at which positive charges can repel new charges, etc. Much like we were talking about making the separation smaller in capacitors. In a capacitor, we have moved negative charges close to the positive plate, which partially shields them, so we can pack more charges into the plate. All told, this is to say, the presence of a dielectric always increases the capacitance of the device. The lowest capacitance of a device is when the space is filled with vacuum, to the extent you can fill something with vacuum, but if there's nothing in the space. A different way to look at this is that since delta V across the capacitor is E times D, and we reduced E, we reduced the potential difference. But of course the charge is the capacitance over, or the capacitance is the charge over the voltage, so by decreasing the voltage without changing the charge, we've increased the capacitance. This factor by which the capacitance increases is different from material to material. We call it the dielectric constant of the material and symbolize it with the Greek letter kappa. A couple of things to note. Kappa is not a K. Get in the habit of writing it distinctly, otherwise you will confuse people and that will go badly for you on exams. You can kind of draw it as a very tiny capital K. It's pretty close to that, but not really. Kappa has no units because it ends up being defined as the ratio of my new capacitance to my original capacitance, the vacuum capacitance. And so therefore it's a capacitance over capacitance. It is dimensionless. Realistically, C0 should be the vacuum capacitance, but for most things, air-filled capacitor would be pretty much the same because kappa is an incredibly tiny number. It's very close to 1, and so we won't notice the difference. In time-honored tradition of textbooks, here is a chart of various capacitance things. By definition, a vacuum has 1, and we can see that air has very close to 1. Plastics and such, plastic, Teflon, or Pyrex or paper, they're sort of in the small handful of digits, 2 or 3 or 5. For whatever reason, your book lists the highest is strontium titanate, which is 300. I don't know why it's so easily polarized. And then there's also, they put in here water. Water is easily polarized because it is, after all, already a polar molecule. If we have oxygen, we have hydrogens like this, and there is already polarization. So it's very easy to move these around to flip their orientation so as to make it polarized. So since it's highly polarizable, it means that it is effective at canceling the field, and so therefore has a high capacitance. All right, sample problem. Capacitor is charged by being connected to a 24-volt battery array, which is then removed, so the capacitor is isolated again. The space in the capacitor is filled with a fluid, and the voltage is now measured to be 16 volts. What is the dielectric constant of the fluid? So remember that kappa is new capacitor over vacuum capacitor. And we know that the capacitance is proportional to the capacitance would be the charge we had over the new voltage, and the original charge would have been the charge over the original voltage, but the charges would be the same because it's isolated. So we end up here with original voltage over new voltage, 24 volts over 16 volts. Kappa is 3/2.